Good morning, Year 12, and welcome to the first session of the 26th of March 2020. Today you'll be looking at exercise 6H, applications of our differentiation of logs, and I want to go through a few different questions that aren't in your textbook, but probably more the kind of questions that we'll get in our examinations as we go through. However, these are definitely enrichment questions in your textbook, and it's definitely worth going through, and we'll look at them soon. So I wrote down a few questions, and I just wanted to look to see what we've got. So the first thing is, I talked about our derivatives of log base e of x, okay, but we didn't prove that it's 1 over x, and the proof we just wanted to look at is how it relates to our exponential function. So that is, we know it relates to our exponential function, and we're going to do that because we know that y equals ln x is the same as log base e of x, and we know that this can be changed, swapped into our other format where we know that this is the log base e of x, and we say the word base e because we change this so it's the base of e to the power of y is equal to x. So we rearrange this to be, e to the power of y is equal to x. I might actually just write x on the other side. It's the same thing. However, then with doing this, we will then work out what is dx dy, and then we can then work out what dy dx is, because it's the reciprocal of that. So in this case here, we can differentiate x with respect to y, in which case the derivative of e to the power of y is equal to e to the power of y. Now, I know that using this in the proof is kind of like a bit how you're going. However, we defined that base e specifically. That number, like 2.7 whatever for e, was specifically designed so that the derivative at that point was 1. Okay, so when we did our exponential function, it had the derivative of 1 at that point. So we've got our exponential function, and the derivative is 1 there. And then, therefore, from this we can find that dy dx is equal to, as we should know, 1 over dx dy. Because instead of dividing by a fraction, we could multiply by its reciprocal, that's why we get dy dx from this, and therefore we can actually write this as 1 over now dx dy is e to the power of y, so we could write it as 1 over e to the power of y if we want. I'll do that, but we know that e to the power of y is equal to x, so that's why we get 1 over x. Okay, so I talked about, and I talked to a few students about what these graphs look like and how it relates to, say, our exponential function. And this is where I've got, say, our exponential function was our graph that looked like this, and we said the gradient at this point is 1, and our log function, which went through 1 across, therefore also had a gradient of 1. And that's why we can see the derivative of dy dx here, when x is equal to 1, is 1. Okay, the gradient here is 1, so it will go through at 1, and it will also cross here at -1, and the gradient of this point here is also 1 of our exponential. And we can also see how it relates to our exponential function as well, because I'll put y and x here, because as we go further to the right, let's have a look at some of these things. So obviously our log function is undefined for anything that x is less than or equal to 0, but if you have a really small number between 0 and 1, we know what the gradient is going to do of our exponentials. Let's have a look and see. So if you have, say, 0.1, if you want to find the gradient of log base x at 0.1, we can just say it's 1 over 0.1, which is 10. So the gradient at 0.1 across is a really steep gradient, which is, at 0.1 across, you can see it's really steep. It's going 10. Rise over run is 10 at this point. And if we put x as 5 across, just say, we can work out that at 5 across it's got a positive gradient, but it's not going up as much. So when you're 5 across, it's only got a gradient of 1/5. Okay? How that relates. So let's have a look at the kind of questions that we will get. So this is the first one. Find the equation of the tangent to our y is equal to ln of 5x plus 1 at x is equal to 0. Okay, normally our log functions are not defined at 0, but this, you can see it has a translation, and it's also got like a dilation as well. This, firstly, we probably should know how to graph this function. And I would actually write this function as, if I'd want you to put this function in the form y is equal to ln of 5 of x plus 1/5. I'd actually factorize this part from that, and the reason why I'd want you to do that is if you looked at your syllabus, our Year 12 part of our syllabus, graphing techniques, we should know how to apply our transformations of the logarithmic functions, as long as a bunch of other things, and we want to put this function as a, our dilation, and plus b, our translation, left or right, in this format, a brackets x plus b. So in this case here, the dilation is being made, as well as the translation that we would do first with that. So this graph here, it's moving across. It's going to only move across 1/5 to the left. So if I actually, whoops, that just messed up. If I actually did a graph for this part, it's only going to have a asymptote going across at negative 1/5, of course, because it's only been shifted to the left 1/5. It's a plus 1/5, and that's why we've got this. It's because, yeah. So, and then we've got the 5. That was squashing it in. So I should say the whole graph would have been moved across -1, but then because it's been squished by 5, it's been pushed into the -1/5 as the asymptote. Okay, and now the other thing is, this graph is going to go through. It's going to go up like this, and it's only going to go normally from the asymptote. The graph would go across and be 1 across to where it hits this x-axis. Okay, so I mean, in the first example, this is a distance of 1 from 0 to 1 there. However, because of this dilation, it's been squashed. The distance here is why it's only 1/5. So this is our dilation. I just want us to recognize that it would go through at 1/5, and this is what this graph would actually look like here. Okay. So therefore, we can actually look and then see if this actually goes through at 0, 0. So, we actually should find this when x is equal to 0. We would say y is equal to ln of 5 times 0, plus 1, which is ln1, which is 0. Sorry, I was looking down a bit. But therefore, it goes through 0, 0. Now, we know we need to find a point in these tangent or normal questions because we generally will use the point gradient formula. I won't in this case because I know it will be a y equals mx line anyway. There's no plus c, or the plus c is 0 going through. Okay, so our next part we would want to do, we've found the point, we need to find the gradient, so we want to differentiate y equal to ln of 5x plus 1. Okay, so we'll say dy dx is equal to, now remember what it is, from this part, this is f of x, and from last lesson on our formula, we found the derivative of this function is f dash of x over f of x. Okay, so I'll put that as the over f of x first, and our derivative of this will go at the top, which is only just 5. Okay, so this is our dy dx, and therefore when x is equal to 0, we can find dy dx, which is equal to 5 over 5 times 0 plus 1. So that's just 5 over 1, which is 5. Okay, and I'm not going to do the point gradient formula for this. If it goes through this point and has a gradient of 5, it's the tangent is actually a line of y is equal to 5x, or we could write that, of course, as 5x minus y is equal to 0 now form. Now notice this graph doesn't look like a gradient of 5, okay, but it's just because it's been squashed. You know, I might be able to select it and squash. Oh, can I squash it? And squash it in. So that's what it really looked like, because the graph is the same as this part. However, it's been squashed in, and that's why this one had a gradient of 1 at that kind of point where I was passing through. This one has a gradient of 5 because of that dilation, and that's where we can see this gradient here going through that point, that tangent, then therefore has a slope of 5. The third question I put is find the normal. Okay, so that's, you know, perpendicular to the tangent to ln of x plus 1 over x minus 2 at x equals 3. I did forget to say, I recommend that you pause the video at each of my questions and then see if you can work it out before I go through it. You know, that would be good practice, but if you have no idea, then just listen to see. Okay, so find the normal. I should check that this is still recording. That's good. Find the normal to this at that. Okay, so firstly, just like the last question, we want to say when x is equal to 3, we can work out what y is. Y is going to equal to ln of 3 plus 1 over 3 minus 1. So ln of 4 over 3 minus 2. Okay, 4 over 1, so it's ln 4. Okay, that's not going to simplify, so therefore I'm just going to say it goes through 3 across is ln 4 up. Okay, wherever this graph goes, this is not going to look like a basic and normal logarithmic function. Okay, it's not just going to look like our basic ln function. So for example, if you have x is negative 10, you'll have ln of 9 over negative 12. So that would be ln of a negative number. So that wouldn't therefore be defined. So there's a bit of play with this. So you wouldn't be asked to graph that. Okay. But the next thing is how are we going to differentiate this? Okay, how are we going to differentiate this? And we should use our log law, which would be if y is equal to ln, well, I'll put the log law over here first. Remember, if it's any log of a over b, okay, we've got, that's the same as ln a minus ln b. ln a minus ln b. So this is probably what we'll use for this, and then we could differentiate each part separately. So in this case here, I will say that ln of x plus 1 over x minus 2, which is equal to ln of x plus 1 minus ln of x minus 2. Okay, so I will use these, and therefore dy dx, let's just do them separately, is ln of x plus 1, so the derivative of this is what is f of x, so x plus 1 is in the denominator, and the derivative of that is 1, and the derivative of that is 1 in the numerator, and then that's minus the other part, which is x minus 2 over 1 as well. I probably wouldn't leave it in this form. We know starting even from the start of year 11, we wouldn't leave our answer like that. So I'll put them together. So this is going to be x minus 2, I'll just cross multiply, minus x plus 1 over x plus 1 by x minus 2. You could do that the slow way if you want, multiply this by x minus 2 over x minus 2, and this is x minus x by x plus 1 over x plus 1, but I'll just put it just like this, and now I can see that x minus x will cancel out in the numerator, and then it's negative 2 minus 1, so negative 3 over x plus 1 by x minus 2. I didn't find the answer because it's when x is equal to 3, so when, running out of space, when x is equal to 3, dy dx is going to equal to, what's that, negative 3 over, I'll just put this as one line, it's 4 times 1, so negative 3 over 4. Okay? Remember, that's not the gradient because, that's the gradient of the function at that point. However, we want to find to the normal of the function. Okay, we want to find to the normal. So therefore, m of the normal is going to equal to negative 1 over that negative 3 over 4. Okay, which is the same as, remember, you're going to change the sign, which is, it's going to become positive, and then we're going to flip that, so it's going to be 4/3. Okay, so m of the normal is 4/3, and now, therefore, using the point gradient formula, we can actually put those two things together. So, using point gradient formula, we're going to use y minus y1 is equal to m by x minus x1. Okay, I probably should put it in the general form for you. It looks like it might get a little bit messy, but y minus the point y1 was, I think it was ln4, wasn't it? ln4. So y minus ln4 is equal to m, so 4/3, over x minus 3. Okay, we can't leave a fraction in our general form, so I'll multiply both sides by 3. So 3y minus 3 ln 4 is equal to 4x minus 12. Okay, and then I have to make sure I can't put this all to the left side and have a negative 4x, so I'm just going to write it, move it all that side and then make it equal to 0. So it will be 4x minus 3y and then plus 3 ln 4 minus 12 is equal to 0. Okay, notice that the constant term for our general form is actually 3 ln 4 minus 12. You know, that you could write in brackets if you want to just put it in black. That's in brackets because that's actually just a constant number. That's ln 4. You know, 2 to the power of what gives you, or e to the power of what gives you 4, 2.7 something to the power of something. It's a constant. Okay. The final question I just stole from the Maths in Focus exercise 503. It doesn't really use differentiation of our logs, but we really need to understand these application questions and see what's going on. So we just have been given this one in a different format when we've been given our log. It says the formula for the time taken in years for kangaroo population growth on Kangaroo Island is given by t is equal to you know, this log function over 0.021. Okay, so this is, if we wanted to graph this, we could work out, given a population, what time it takes to get to that population. That's, I mean, that's not that useful, but we'll have a look and see what actually we want to do with it. Okay, so firstly, A, what is the initial population? So this is, we're going to say, for A, we're going to say when time is equal to 0, we'll find our initial population, isn't it? Okay, so we're going to get, I'll just write 0 is equal to ln of p over 20,000 over 0.021. That's a really messy line there. Okay, and we would want to solve this for p. Okay, so multiply both sides by 0.021. Well, the left-hand side is still going to be 0, so that's just will go away, pretty much. And we would therefore get, I'll just write it the swap the sides. We'll therefore get ln of p over 20,000 is equal to 0. Now I look at this and I can see two ways. Should check that my sound is working. Good. I can see two ways I could solve this. So the first way is using our log law like before. That's probably the harder way. I might do the easier way first. Because this is log base e of this, I could just use my rules and say e to the power of 0 is equal to p over 20,000. So just converting this, but anything to the power of 0 is 1. So that means 1 is equal to p over 20,000, and then I would times both sides by 20,000. I'll just swap them as well and get p is 20,000. That's probably the easiest way of doing that. Okay, I'm looking. Yeah, of course you could do it the other way. You know, I'll put or. If you want, you could have also solved this by saying, using that log law, ln of p minus ln of 20,000 is equal to 0, and then added the ln 20,000 to both sides. So ln p is equal to ln 20,000, and then took, say, the raised both of these to the power of e, you know, which cancelled out, and we got p is equal to 20,000. Okay, so these would end up, you know, cancelling out, as you can see. Ln of what equals ln of 20,000. You know, ln of 20,000 is equal to that. So the initial population was 20,000. Find correct to one decimal place the time it takes for the population to grow to 25,000. I'm not going to do both of these. I don't even think I'll type this in the calculator for you. But for the population to get to 20,000, you're trying to find the time. Actually, I won't even write it down. Time will be equal to ln of 25,000 over 20,000, and then divided by 0.021. That's, you could just put that in your calculator to get that answer. C, change the subject of the equation to p. Okay, so we've got, I'll write this down the other way. So this is b. I'm going to write it down as ln of p over 20,000 over 0.021 is equal to t. And taking a few lines, but from this I would multiply both sides by 0.021. So ln of p over 20,000 is equal to 0.021t. Okay, to remove this ln, okay, I'm trying to just get p, I'm just trying to shed off everything. I'll raise both sides to the power of e, or I'll make e to the power of both sides. So I'm going to put, you know, that would cancel out this here. Or of course I could just, the way you do that is just changing these. You know, this is e to the power of that is equal to that, right? So that's what we're just writing this as. P over 20,000 is equal to e to the power of 0.021t. Okay, this is just not even raising them to the power, it's just changing the form, and then I would times by 20,000. So P is equal to 20,000 e to the 0.021t. Okay, we can see that's our exponential function. This is a like, you know, this would change our, say, you know, dilation. It's not going to go up as fast. And this is our starting point. So when time was 0, e to the power of 0 is 1, so that's why we got 20,000 as our first answer. It's our exponential function that we would want to look at. The next one is hence. It will say hence or otherwise. Find correct to the nearest whole number the average rate of change in population between 2 and 5 years. So let me put a graph. Let me just put on Google GeoGebra. So, you know, if you're looking at y is equal to 20,000 e to the power of 0.021 x. Oh, zoom out. I need to get to 20,000. Okay. So here's my exponential function. Okay, it's absolutely crazy. I might just not even bother with that. I was hoping to. But what this question was asking, if I just do another graph of this, the average rate of change, this is not the instantaneous rate of change. Okay, this is the average rate of change. So just here, average rate of change. So we're just finding that by just finding what is the population when it's 2 years, when time is 2, what's the population when time is 5, and then we'll just find the rise over run. Okay, so if you had some exponential function Okay, just say it's going up like this. You know, when time was 2 across, what is the population? When time was 5 across, what is the population? And therefore, the average rate of population is going to be rise over run. So you might have went up 50,000 divided by 3, isn't it? That's a thing of 3. So that's what how you would tackle that kind of problem. I won't go through all of it. And then find correct to the nearest whole number the rate at which the population is growing. So this is now instantaneous. It's not talking about average at all. So this is actually going to find the change in population with respect to time. So for E, that's totally not B, wasn't it? But for E, we would find what is the derivative of P, what is change of P with respect to time. Okay, so that's going to be actually the derivative of an exponential function, which is 20,000 times our derivative of this, and we know that's 0.021 will get multiplied forward. So 0.021 times e to the 0.021t. Okay. So 20,000 times 0.021 is 420. 420. Yes, e to the 0.021t, and then you would say when t is equal to whichever these questions are, I won't do them, but when t is equal to 3, you could calculate what the instantaneous change in population is, and if t was equal to the others, you could do the same thing. The final thing, I feel like I've been talking for so much of the session, but the final thing I wanted to talk about was in your book. Let me find it. It starts to talk about dominance. The dominance of our function of like x ln x, or the dominance for our function of ln x over x. Okay, so with these, this is, when we're talking about dominance, this is talking about, for example, if we graphed a y is equal to x squared, just say x squared plus x kind of graph, and we say this function, because it's an x squared, it's always going to start high and end low, because it's a positive, start high and end high, because it's a positive x squared. And the reason why is because as x approaches really large numbers, or really, really small numbers, this number, x squared, is going to dominate our x. So for example, when x is 20, that's not a very big number, but 20 squared is going to be way more than 20. Okay, so you're looking at, what's that, 4,000 compared to 20? 400, I think. And this is how we deal with our polynomials. So in this part here, if we typed in, say, x is a number like 5, when x is 5, then ln x, I could put on my calculator, ln of 5 is a smaller number than 5. So as x approaches, 0 from the positive direction, what's it saying? This is getting, as it approaches 0, it's going to approach 0, but as it approaches infinite, these are looking silly. I don't know why it says 0 plus there. Okay, but as x ln x approaches infinite, both those numbers are going to increase, so of course it's going to be infinite. Okay, but for this one here, this second graph, as x approaches infinite, as the numbers get larger, this number, the numerator, is a smaller number than the denominator. So the number's going to get, it starts to approach 0 as this number gets much larger. So that's saying the x becomes a much larger number than ln x. So as you're getting a really big number, this is not as big as that, so it starts to approach 0. It becomes a kind of insignificant number over a billions kind of number as we do that. And that's just the word dominance I wanted to talk about. I might leave you there. Can you please have a look at 6H? I'll just scroll through the questions so you can see I'm sure if you wanted to pause it at that point, but that is our exercise 6H.